A confirmation about the audio, please, guys. If the audio is clear and available, kindly confirm the same. Thank you. So, hello, a very warm good evening to all of you, and welcome to Baiju's Exam Prep IAS. Welcome to the final session of this particular year, not the final session of geography. After this particular session, next week, I hope when we'll meet, it will be the new year. So, basically, today we shall be continuing our discussion from the portion of climatology where we left off yesterday. Yesterday, we have had a basic discussion about the evolution of atmosphere. We had discussed about the various different components and constituents of the atmosphere. What do we understand by the basic of the greenhouse effect? What is the long wave terrestrial radiation, the short wave solar radiation, the purpose solved, and the role played by each of the components that constitute the atmosphere. So these all details we looked at yesterday. Now we had started the discussion for the portion of the layers of atmosphere, where we have had a discussion about the region of troposphere as well as the region of stratosphere. Now, in the portion of troposphere, we observed that troposphere basically is the one which exhibits a positive lapse rate. Positive lapse rate. That means temperature higher up is lower. Temperature is higher near the surface and reduces as one moves up. So that is the positive lapse rate that we observed. So that means the top of troposphere is going to indicate a low temperature, significantly low temperature to the tune of minus 60 to minus 80 degrees Celsius. To that extent, the temperature can reduce as we go to the top layer of the troposphere. Now, in the case of the stratosphere, we observe that because of the presence of ozone layer, which is also referred to as the ozonosphere. Now, in stratosphere, you have the presence of the ozone layer. This is the ozonosphere. Now, we observed and we found out that in this region of ozonosphere, the ultraviolet rays of the sun, they are basically absorbed substantially, and they are also reflected back. Okay, so these ultraviolet rays, because they are trapped in the ozone layer and basically they are reflected back from the ozone layer, that is why there is an increase in temperature. So stratosphere ends up indicating a kind of a negative lapse rate. Negative lapse rate. Now, what does that indicate? That temperature increases with height. Temperature increases with height. So as you move higher up in the stratosphere, the temperature will start to increase. And by the time that you reach the top of stratosphere, you might experience a temperature around 0 degrees Celsius or -1, -2, or somewhere in that region. Because at the bottom of stratosphere, the temperature is around -60 degree, -70 degrees Celsius. So there is a marked increase of temperature in the stratosphere. So stratosphere, because of the ozone layer, again becomes a source of heat generation. Just like the ground surface becomes a source of heat generation for the troposphere, stratosphere, by trapping the ultraviolet rays and the ultraviolet rays spending so much time in the region of the stratosphere, it starts becoming a source of heat generation. Lot of heat is generated there. Now, if we talk about the region of tropopause, tropopause basically lies between the stratosphere above and troposphere below. Stratosphere above and troposphere below. Here is where you find the tropopause. Okay, so tropopause basically is that zone of transition. Now here, understand that stratosphere experiences warming. The top layer of the troposphere experiences cooling, because by the time that you reach the top of troposphere, you will have a temperature in between around -60, -80 degrees Celsius. So here, the top of troposphere is cooler. So in this layer, there is warming from above and cooling from below. So in a way, equilibrium is attained in the region of tropopause because there is warming from above, there is cooling from below. So in the region of tropopause, there is a kind of an equilibrium. That is why tropopause does not indicate any kind of change in temperature. It indicates what is referred to as the zero lapse rate. Zero lapse rate. That is, temperature remains constant. Okay, so that is the case of tropopause. So same is the case in stratopause also. A similar situation you will observe in the region of mesopause also. So troposphere, a positive lapse rate; tropopause, a zero lapse rate; stratosphere, a negative lapse rate. Now, as I told you, stratosphere becomes a source of heat generation. So because of trapping of heat due to trapping of UV rays and its reflection, tropopause, or rather stratosphere, becomes a source of heat. Okay, now when you reach the region of mesosphere, you are again moving away from the source of heat, right? Just like in the case of troposphere, as you would move away from the land surface, you are moving away from the source of heat. Again, in the case of mesosphere also, which lies above the stratosphere, as you move higher up in mesosphere, you are moving away from the source of heat. So here again, you will experience a kind of a positive lapse rate. Positive lapse rate. Okay? And positive lapse rate will again indicate that temperature reduces with height. Temperature reduces with height. Okay. Now, just like in the case of tropopause, stratosphere also has the end demarcated by the stratopause. And just how in the case of tropopause you had a zero lapse rate, here also you will have the stratopause indicating a kind of a zero lapse rate. Now, here, the temperature starts decreasing with an increase in altitude and reaches up to minus 100 degrees Celsius by the time that you reach a height of 80 to 100 kilometers. The temperature can reduce up till minus 100 degrees Celsius. So, there is a marked decrease in temperature which is observed. So, here, what you observe is the scenario that the temperature is going to reduce. Let's suppose this is the mesosphere. This is the mesosphere. So at the base of mesosphere, you might have a temperature of 0 degrees Celsius. By the time that you reach the top, you have a temperature of minus 100 degrees Celsius. So if I ask you a basic question, as you come from the top of mesosphere to the bottom of this mesosphere, the temperature is going to increase, or is the temperature going to decrease? As you come from the top to the bottom, the temperature is going to increase, or is the temperature going to decrease from top to bottom? This is a very basic question. I expect all of you to get the correct answer for this. Still around 26% of you believe that the temperature will okay. Minus 100 degrees Celsius is lower, or 0 degrees Celsius is, which is colder? Minus 100 degrees Celsius or 0 degrees Celsius, which is colder? Okay, in this we are clear. Girish, okay. Always minus negative will be always be lower temperature. Why is there such a kind of a confusion in this? Are we aware that negative temperature means colder conditions? Okay. Girish, is there any confusion in that about 0 and minus 100? Please understand, this is a very basic thing. Colder sub-freezing temperature. So as you come into the lower regions of mesosphere, there will be a kind of an increase in temperature, always an increase. So imagine an object which falls from outer space or somewhere. Now, as this object hurtles down in the mesosphere, it will experience a higher temperature as it comes down, right? As it covers the distance in the mesosphere, it will experience a higher temperature. That is where the meteors, meteorites, etc., that you observe that it burns up into the sky, it happens in the region of mesosphere. So any falling object, it experiences a higher temperature as it falls down because of positive lapse rate. And that is why meteorites, etc., will burn up in the region of mesosphere itself. Okay. Bijaya, okay. Is it your first class, my dear friend? Is it your first class that you are attending? Is everybody comfortable with the color of the pen? Ankush, no, it varies. Everybody is comfortable with the color of the pen? Okay, fair enough. So these minor things I hope can be taken care of. Shelja, in ancient times, the amount of oxygen was not so much and it will increase day by day. then sir, can we say it will be increasing more in future? No, we cannot make a prediction like that, because you might have a sudden volcanic activity across the entirety of the planet, and again carbon dioxide will increase. Okay. Now, up till the region of mesosphere, you have almost a kind of a uniform concentration of oxygen, nitrogen, and the various different gases. They are present in uniform concentration. But beyond the region of mesosphere, the gases, they are present in a heterogeneous mixture. They are not present in a homogeneous mixture anymore. You might have certain pockets having some amount of nitrogen dominant. You might have certain pockets might having oxygen in dominance. So above the region of mesosphere, you are talking about a height beyond 100 kilometers from the surface. So at a height beyond 100 kilometers from the surface, you will have a random distribution of gases such as oxygen and nitrogen. And there, the density of gases will be very less, not at all adequate for breathing, etc. So that is where the density will also be very less. Now, up till a stretch of almost 400 kilometers, there will be significant amount of these gases which will still be present in some bulk quantity. Beyond that, you might have random, a couple of molecules present here, a couple of molecules present there. So up till a height of around 400 kilometers, you still have, even above the mesosphere, you still have the presence of oxygen, nitrogen, and these kinds of gases. Now these gases, they are bombarded by the unadulterated rays of the sun, undiminished rays of the sun, and basically the solar rays consisting of x-rays, ultraviolet rays, everything will bombard them. And that is when the molecules, they become excited, in the sense that an electron might be gained, an electron might be lost by the atoms. And whenever that happens, you have the creation of a charged particle, a charged atom, which is known as an ion. So, located above the mesosphere up till a height of around 400 kilometers, you have a dominance of these ions and ionic structures, where the atoms, when they get impacted, again I will repeat, when the atoms get impacted by the unadulterated rays of the sun, thereby the electrons can either leave their natural state, an electron can be gained by an atom, thereby leading to a significant amount of charge being developed there. So you have an entire layer or an entire region where charge develops. Now, there also in the lower portions, there will be a kind of a perpetual charge which will be developed because of greater concentration of oxygen, nitrogen, and so on. It varies. Even this ionosphere, it is not homogeneous. You have a further classification of ionosphere as D layer, as E layer, as F layer, etc. But that is not something which is required for your general studies portion. So we'll not go into the details of the parts of ionosphere or the various layers within the ionosphere. But just the basic ideation would be sufficient, that above the region of mesosphere up till a height of around 400 kilometers, where you still have some dominance of oxygen and nitrogen, the unadulterated rays of the sun, they will be exciting these atoms to a charged state. And the formation of ions in this area is what renders the name as ionosphere. That is why in this region it is referred to as the ionosphere. So ionosphere is located between 80 to 400 kilometers above the region of the mesopause. It contains electrically charged particles known as ions. Why electrically charged particles? Because of the influence of the X-rays, ultraviolet rays, all the power of the sunshine. Now, this particular presence of ions helps in reflection of the radio waves. So presence of ions reflect the radio waves back to the surface. And this reflection of radio waves They help in facilitates radio communication. Unadulterated and undiminished means that it is all powerful, because by the time that the solar rays they come through the mesosphere, the stratosphere, etc., they diminish in terms of their intensity ever so slightly. X-rays, for example, they end up getting filtered out within the region of mesosphere, some portions of it in the region of stratosphere itself. Then even beyond the mesosphere, the X-rays get filtered out. And then when we talk about ultraviolet rays, they are trapped in the region because of the presence of ozone gases, ozone molecule. And that is where the stratosphere becomes hotter. So on the ground surface, you receive a diminished amount of solar rays, but above, you receive a kind of a complete undiminished power of solar rays. Okay. Ankush, UV rays and sun rays are heating ionosphere and stratosphere. But why not mesosphere? See, understand, it is not as if only the mesosphere is not getting heated up by the region, by the UV rays. Please understand that mesosphere is getting cooled down. Mesosphere is a colder layer. That is why by the time that you reach the top of mesosphere, the temperature is around minus 100 degrees Celsius. Beyond the region of mesosphere, where the density of the gases are very less, you might have a random pocket of concentration of gases that will get excited because of the energy provided by the rays. That is why certain pockets will indicate a higher temperature in the region of what is referred to as thermosphere. In the stratosphere, the only reason that the temperature is higher, the only reason why it heats up the stratosphere is because there's a trapping of ultraviolet rays because of ozone molecules. Had the ozone molecules not been present, even stratosphere would not be warmed up. So thereby, that is why in the region of stratosphere you have a higher temperature, which is an aberration. Otherwise, from the surface upwards, right up to the top of mesosphere, you will observe a consistent reduction in temperature. Only that portion of stratosphere is an aberration because of the presence of ozone molecules. Okay. And Vishal, every pause area have zero lapse rate. Why ionosphere is also called as thermosphere? Ionosphere is not called as thermosphere. In that entire extent of thermosphere, you have a layer which is known as ionosphere. It is not the case that ionosphere is the other name of ionosphere is thermosphere. Thermosphere basically is the one where you have a higher temperature, because the full power of solar rays they fall upon individual bunch of particles. In the region of thermosphere, if you can imagine, let's suppose, for your own imagination's sake, let's suppose we talk about in this area up till the top of mesosphere. This is where the air is homogeneous. Homogeneous. So let's suppose if you have to talk about the distribution of gases in this area, the distribution of gases will be almost, let's suppose, like this. Okay. The gaseous molecules will be distributed in almost uniform proportion: 78% nitrogen, 21% oxygen, a uniform amount. Above this, you have what is also referred to as heterosphere. So here you have heterogeneous distribution. So that basically refers to, let's suppose if you can imagine, one portion will have concentration of few molecules here, another set of molecules might be present here, other set of molecules might be present in this manner, and here you might have a dominance of nitrogen, here oxygen, here maybe again nitrogen, or here a mixture of oxygen nitrogen. So you don't have a uniform mixture. That is when you have the power of the unfiltered solar rays hitting them. These pockets will get excited quite significantly and they will indicate a higher temperature. That is why it is the thermosphere. Within the thermosphere, you have that layer which is the ionosphere. Within this thermosphere, you have ionosphere. Okay, I hope this is understood. Kármán line basically is to the top of the homosphere or to the top of the mesosphere. That is what is referred to as the Kármán line. Okay, and then Deepika, how mesosphere or how meteors burn only at 0 degrees. See, don't think about it that the meteor is burning at 0 degrees Celsius. So it is freezing. So how is it burning at 0 degrees Celsius? No, the meteor is falling. So in small distance, let's suppose here the temperature in this area, let's suppose here it is somewhere to the tune of, let's suppose it is higher. But as the meteor falls, there's a frictional force associated. Frictional force generates its own heat. That frictional force, when it generates its heat, that will also start burning. And then within the entire extent of mesosphere, as the meteor is falling, it is experiencing a rise of temperature by almost 100 degrees Celsius while falling from -100 to almost zero. That is a temperature difference of almost 100 degrees Celsius. And that 100 degrees Celsius temperature change is quite sufficient to lead to burning. Okay, I hope that is understood. Ankit, is that understood? GIB, Ankush understood. Vishal, Deepika, Ashish. Ashish, your question was that is there any possibility of development of electric current in that area? See, the charge needs to flow, and the continuous flow of charge is the only thing which can generate an electric current. Here you might have a transient movement of charge. So for example, it is also in this area of ionosphere where you can experience auroras to be formed. You have some unique phenomena such as space hurricanes. Okay, so where you have the charged particles from the sun induced by the magnetic field of planet Earth. These charged particles interact with oxygen and nitrogen in this region of ionosphere also, and they produce beautiful hues of coloration. Okay, so that is something that you will observe. I read that meteor burned due to the fraction to the air. Friction, you mean? Yes, obviously. As the meteor is coming down, it will experience that frictional force, the air resistance, which will increase the temperature. Ionosphere lies within the region of thermosphere itself. Okay. Hole in ozone layer is basically where the concentration of ozone is so very less, the ozone layer is so very thin that it is not able to filter out the ultraviolet rays. The ultraviolet rays of the sun, they pass through. So that is what is referred to as the ozone hole. Okay. Yes, GIB, that is correct. Okay. So now we come to the portion of insolation. What is solar insolation? So insolation is different from temperature. What is insolation is basically it is the amount of solar radiation received on a given surface in a given period of time. The total amount of solar rays which fall upon the surface for a given period. That is solar insolation. Okay. Now, it does not directly impact the temperature experienced in an area. Temperature experienced in an area is dependent on a wide variety of factors. It does not directly influence the temperature in an area. Having said that, it is an important factor in contributing to the temperature. So, here, basically, insolation, when we talk about insolation, does not directly define the temperature in an area. I will still have candidates asking me about the same question. I'll bring you back to the same line that I have written, but try to internalize it. Insolation does not directly define the temperature experienced, but is an important factor in determining the temperature. What this virtually means is basically a region having having higher insulation can exhibit lower temperature, and also a longer duration of solar insolation in certain areas can still mean lower temperature. For example, if we talk about, let's suppose, the region around equator. Now, at the region of equator, the sun is almost vertical, closer to verticality, or the sunshine is very high through the year. But in the day, let's suppose you talk about the duration. So, significant amount of cloud formation is observed in the equatorial areas, almost daily occurrence of rainfall in the afternoon and the evenings. So, these clouds will block the sunlight. But still, these equatorial areas will be very hot. But when we talk about the polar regions such as the Arctic and the Antarctic, for example, right now, presently, the region of Antarctica is experiencing continuous sunshine, right? But does that mean Antarctica will become very hot? No, even now, Antarctica might have a temperature of -5, -10 degrees Celsius in the coastal areas, and in the interior, it might be even lower. So, what it tells you is that insulation is just one of the factors which influences the temperature. But temperature can be high or low, regardless of the factor of insulation, and it is contributed by other important components as well. Okay. So, here, when we talk about insulation, places across the planet, they receive various degrees and various amounts of solar rays. So, the solar insulation received in different areas can be quite variable. And that variability is defined by certain factors. One is angle of inclination of Earth, right? So the Earth is inclined on its axis by an angle of 23.5 degrees, which means different places, they have varying amount of exposure to the solar rays. Okay. Revolution of the planet around the sun, which means there will be one position where the planet is farthest away from the sun. There will be a position of perihelion where the planet is the closest from the sun. So that proximal variation in the distance between the Earth and the sun, that can also lead to variation in solar insolation. Then the direction in which the land is facing, for example, a mountain, a plateau, a sloping area, if it is directly facing the sun or is it away from the direction of the sun, or even altitude. So these factors will end up influencing the amount of solar insolation received in a certain place. So let us take a look into these factors in detail. Okay. Now, here, when we talk about the angle of inclination, so this is a major factor when it comes to the intensity of sunlight. Now, planet Earth is tilted on its axis by around 23.5 degrees, right? It is tilted at an angle of around 23.5 degrees. That is the axial tilt. Now, this axial tilt basically means what? That here on the surface, the solar rays, they fall at different angle. The earth being a spherical object also means that different areas, they experience different amount of solar insolation. You have periods where the region of Arctic, for example, right now during the winter in the northern hemisphere, the region of Arctic would be in perpetual darkness. Antarctica would be in perpetual light. So you might have this local variation also, aided by the angle of solar or the angle of the actual tilt. Now, here you have to understand one basic factor. For example, wherever or whenever the solar rays, they fall directly or they are perpendicular, let's suppose, take the torch experiment. Okay, let's suppose the solar rays, they fall perpendicular, right? Now, in comparison, if you consider the torchlight, which is slightly inclined, let's suppose the torchlight which is inclined. In this case, the pathway covered by the torchlight is this much, and in this case, the pathway covered by the torchlight is larger. The Pythagoras theorem, the diagonal is always larger. Now here, if I talk about the position of torch A and this position of torch B, which will have more amount of power, which it will more amount of power in terms of energy on the ground surface, which will indicate more power. Very good. Always A. Always A will be the one where directly there will be more energy indicated to the ground surface. In the case of B, you have slanting rays which cover a larger distance through the atmosphere, so they get diminished. That is why in the morning, basically, these all things should come by natural logic, guys. So in the morning, when you see the sun rise, the sun is shining, but it is slightly cooler. In the evening, the sun is still shining, but it is slightly cooler. In the afternoon or during the noon time, the sun is vertically upwards and it is very hot. Have you ever thought about it, that why mornings get cooler? Why is it that the sun is shining even at 6 a.m., even at 7 a.m., the sun is shining? But it does not heat the ground surface to the same extent as 12 p.m. or 1 p.m. in the afternoon, how it is heating up the surface. Why is it so? I think many of us basically we have like taken this to be a kind of uh, a given nature from the nature outside world itself. Why to put mind in this? So all those who had said that B is going to give more energy, I want an answer for you from you. Why is it that, or if you have ever thought about it at all, that in the early mornings or in the late evenings, even when the sun is there, why it is cooler? Can I get an answer for that? Why? Because of tilt. Reflection. Reflection from where? Still, only those are answering who had basically talked about A as an answer. I won't name you guys, but think about it. Okay. So it is always going to be the case where when the rays are perpendicular, when the solar rays are direct, they will cover a shorter distance. This will cover a shorter distance. Shorter distance means more power, will undiminished power will reach the surface because they will be covering less distance through the atmosphere. Slanting will always cover a larger distance. When slanting covers a larger distance, the solar rays will cover that larger distance in the atmosphere, where they start getting diminished, where their power starts to get diminished. They become weaker and weaker as they have to transit their way through multiple different thickness and the layers of the atmosphere. Okay. Wasn't this thing taught in class 8th and ninth class? Sometimes I wonder these things, that ideally you should ask a question from your school. If you are unable to fathom this simple concept, ask your school that what did you do with me, and where did you land me up. See, it is not about a rocket science or a Schrodinger's equation that you forget. If you forget Fourier's theorem, Laplace theorem, it is understandable that you forget. But if you forget this basic thing that light travels a shorter distance and a longer distance, then that is something which is beyond that extent, right? So, anyways, moving on. So basically, that is where the angle of inclination and the spherical shape of planet Earth ensures different areas they get varying angle of the solar rays. Wherever you have the solar rays covering shorter path or solar rays falling directly, they will cover a shorter path, right? Shorter path as they cover through the atmosphere means they will be less diminished, they will be less reduced, and that is where the heating cost will be quite significant. Okay. Now, then revolution of planet Earth around the sun. So planet Earth moves around the sun in an elliptical orbit, and that elliptical orbit means there will be a position of perihelion, there will also be a position of aphelion. Perihelion, which is generally observed on 4th of January, when the Earth is closest to the Sun. That is when the distance between the Earth and the Sun reduces to around 147 million kilometers. That is the case of perihelion. In the case of aphelion, the distance is around 152 million kilometers. So there is a variation of around 5 million kilometers which happens. Now, that will also influence the amount of insolation received on the surface. Okay, it alters. Perihelion means closest to the sun, not away from the sun. Alters, or simply to write, perihelion position means Earth gets slightly higher amount of solar rays. Slightly higher amount of solar rays, they are received by planet Earth during the perihelion position. Having said that, it is not going to be the case that on the day of perihelion, the entire planet is going to become very hot, and in the time of aphelion, the entire planet is going to become very cold. Okay, before you are typing that question, I know many of you would be typing that question with a great fervor. It is written January. January is very cold. There is something which is wrong. Either you are telling wrong or earlier you had told wrong. Again, I would reiterate that it is not the case that slightly greater amount of solar insolation will lead to an increase, substantial increase in temperature. The actual tilt basically influences the amount of time that a region receives that solar insolation. On 4th of January, the northern hemisphere is going to be tilted away from the sun, right? So despite the fact that planet is slightly closer to the sun, But still, the daytime is very less. The sunrise happens late, the sunset happens first in the northern hemisphere. Daytime is very less, so there won't be much, it will be still a colder condition. So that is why it is not always going to influence the temperature. So this variation of insolation does not mean a variation in temperature, because temperature is dependent on other factors associated. Okay? Now, the other concept or the other particular factor which ends up determining the variation in the amount of insulation received in different places is the configuration of the land. Configuration, by the factor that configuration of the land, what we mean is that the direction in which the land is facing in the northern and the southern hemisphere. Okay, so here the direction in which the land faces, north or south. If I give you a simple illustration of this, let's suppose here, let's suppose here you have a mountain system, let's suppose, beyond the tropics. It is an exaggerated mountain for that matter, but still, just for appearance sake. Now, here, this mountain will have this southern side. This mountain will also have the northern side, northern face and southern face. Let's suppose this is the sun, the solar rays. Now, as the solar rays come into this area, for this mountain, which face of the mountain will receive more direct energy and more direct rays of the sun? The north face or the southern face? Beautiful. It is always going to be southern face, which will experience more direct rays. It is not as if northern face will be experiencing night time. There you will have that shadowy kind of a thing where the mountain perpetually casts a kind of a shadow. Now let's suppose, so here we can say that the southern face experiences greater amount of insolation. Now if I talk about a mountain, again an exaggerated mountain here in the southern hemisphere, let's suppose. Now this will have a northern face. This will also have a southern face. So in this case, in the southern hemisphere, which will receive more direct rays of the sun? The northern face or the southern face? Beautiful. Northern face. So the similar kind of a mountain system, a similar kind of a topography, because of its location, different areas will experience varying amount of solar insolation. For example, when we talk about the Himalayan mountains, the Himalayas, do they lie to the north of Tropic of Cancer or to the south of Tropic of Cancer? Are we aware of this? Himalayas? Okay. Locate the Himalayas in the map. Okay. Locate the Himalayas in the map. Look at where the Tropic of Cancer is. Look at where the Himalayas are. Do this. Himalayas are to the north. Tropic of Cancer passes through almost the central part of the country. I hope we are aware of that. That Tropic of Cancer passes almost to the central part of the country. How many states does the Tropic of Cancer cut through? Are we aware of that? Good. All those who are not aware, including the ones who have given 5, 7, all these answers, kindly do that. This is a kind of a basic thing that you can do. West Bengal, Jharkhand, MP, Gujarat. What about Rajasthan, Chhattisgarh, Tripura, and Mizoram? So, do locate. This is something that you should be aware of. This is not something which needs to be taught in the class. But anyways, so here, Himalayas, they lie to the top north of Tropic of Cancer. We do know that due to the axial tilt, on 21st of June, the sun almost shines vertically over the Tropic of Cancer. Around equinox, the sun shines vertically almost above the equator. In the winter solstice, the sun shines almost vertically over the Tropic of Capricorn here. So this image here, the second image that you see, this indicates the relative positioning of the sun in between the various months. This is during June, this is during equinox, right? This is during the month of December, when the sun is almost vertical over the southern hemisphere. Himalayas are here to the north of Tropic of Cancer. So, Himalayas will also have a northern face. Himalayas will also have a southern face. Out of the northern and the southern face of Himalayas, which will receive more direct rays of the sun? Will it be the northern face of Himalayas or will it be the southern face of the Himalayas? Very good. It will be the southern face of Himalayas, which will receive more direct rays of the sun. Okay, the southern face of Himalayas will receive a greater amount of solar insolation. More direct rays from the sun will be received by the southern face of the Himalayan mountains. That is why the southern face of the mountains of the Himalayas, they still have greater number of habitations, human habitations. Northern faces also have human habitations, but lesser in quantity. Generally, greater amount of human habitations in the entirety of the Himalayan valleys, Himalayan hill stations. Most of them you'll find to be present on the southern face of a mountain rather than immediately to the northern face of the mountain. Okay, so that is where the configuration of land or the direction in which the land is facing also has the power to influence the amount of solar insolation which is received in an area. The other factor is altitude. Amount of solar insolation increases with altitude. Regardless of the temperature, the amount of solar insolation increases with altitude. And the reasoning here is very simple, guys. Think about, let's consider the plain area, and let's consider the Himalayan mountains and the Tibetan highlands. Now, these Tibetan highlands or plateaus are at an elevation of 5 kilometers from the surface. Now, the solar rays which have to reach the sea level and the solar rays which have to reach the Tibetan highlands, in order to reach the sea level, they have to cross the broader extent of the atmosphere, isn't it? They have to cross the broader thickness of atmosphere in order to reach the sea level. But in the case of highlands, they have to cover the lesser distance. That is why with greater altitude, the power of the solar rays are very high. This is one of the reasons why when you go to a very great height, let's suppose the top of a mountain, etc., if you don't have protective clothing, you might get a sunburn. I understand for many of us, sunburn basically is indicative of very high temperature, but that is not sunburn. Okay, sunburn is not caused because of very high temperature. Even under very low temperature, if there is overexposure to sunlight and bright sunlight, that can also cause sunburn. Okay, so with greater altitude, the amount of solar insolation is higher. And because closer to the ground surface or closer to the sea level, more atmospheric particles come in the path of the solar rays. So the solar rays, they get diminished. Okay, right? Okay, I was expecting this question. So, Kaushik, read this statement again. The question is, why does it not cause high temperature in high altitude areas? Because insolation is just one of the factor. In the high altitude areas, the density of air is very less. So that is why the heat is lost very easily there. The heat is not retained or trapped for a longer period of time. I hope we are aware that if you reach or if you go to the top of, let's suppose, those people who climb the top of Mount Everest, most of them, 99.9% of them, they have to take additional oxygen cylinders along with them to facilitate breathing. Breathing becomes very difficult with height because the air density is very low. So if the air density is very low, whatever solar rays are received will easily be lost by the surface. Very quickly, it will be lost by the surface. Whereas closer to the sea level, the high density of air around us ensures that trapping of the heat is done. This is the reason why, despite the higher insolation, the mountainous areas will experience very, very low temperature. Okay? Right? Why sunburn in coastal areas? Sunburn can happen anywhere. Sunburn can happen even the desert areas. So wherever you get an overexposure to sunlight, there is sunburn which can occur. Now, then we come to the factor of albedo. What is an albedo? Now, the simple understanding of albedo is basically when you step outside your house during the afternoon, around, let's suppose, 12 p.m., 1 p.m., 2 p.m. in the afternoon. Now, if you take a look at the black concrete roads or the black tarred roads, and if you try to walk barefoot on them, your feet will start burning. But let's suppose you are walking on a kind of a marble floor. It appears to be cooler, isn't it? If you are walking, let's suppose you have an option of walking on the black road and a grass. You always prefer grasses because they are a bit cooler and soft. Other than the softness factor, they are a bit cooler. Similarly, many of your houses, you would have seen that on top of the buildings, there is that black tarring which is done for waterproofing. Now, during the daytime, if you touch that black surface, it becomes very hot. But let's suppose your building is painted white from outside. You touch that outside wall, it will remain cooler. Why is it so? Because different surfaces, they have different properties in order to absorb and reflect heat. When you start to or try to walk barefoot during the afternoon on bare rocks, barren rocks, your foot will almost start burning. But the same rocks during night time will be very extraordinary cold, right? So different surfaces have different properties for absorption and reflection of heat. That characteristic or nature which defines the variability in absorption or reflection of heat, that is what is known as albedo. So albedo is basically the portion of the solar energy reflected from the surface of any surface back into space or back into the sky. It varies between 0 to 1, between 0 and 1. 0 indicating complete absorption. Obviously, no surface can ever have complete absorption. Complete absorption and no reflection of solar rays. Whereas one will indicate one indicates complete reflection and zero absorption. Now, this can end up influencing the temperature experienced in an area. The variation in temperature of in an area can be influenced by the factor of albedo. How? So, for example, let's suppose you have two different surfaces. Let's suppose, or let's consider the images that you see in the screen here. Now, let's name this as A. Let's name this as B. Out of A and B, which will reflect more solar rays, A or B? B will reflect more solar rays? Okay. On what basis do you think B will reflect more solar rays? Please let me know. Please don't change the answer. There is no learning in that way. I want to understand, why do you think that B will observe, or B will reflect more solar rays? B is cooler. Is the image not clear? Summer and winter, you guys are applying summer and winter concept here. Okay. Everything you are mixing together. A is a hard surface, so okay. A will reflect greater amount of solar rays. Always A will reflect greater amount of solar rays. This is basically, I'm not asking about temperature. Have I asked about temperature here? Have I asked which is cooler, which is hotter? Then also many of you are wrong. I have asked which will reflect solar rays. All of you are coming to the deduction of temperature right from the first go. I've still not come to the factor of temperature. Which will reflect solar rays? That is the basic question. So color is one of the basic indicators and the factors determining what will reflect and what will be absorbed. I hope we are aware of the basic fact that white reflects more, darker colors, they absorb more, they reflect less. So on A, you will have greater reflection of solar rays. Here, you will have very little reflection of solar rays. Greatest amount of absorption of solar rays will happen. That is why ice covered areas, etc., they have an, or snow covered areas and ice covered regions, they have an albedo of, snow and ice have an albedo of around 0.85. Albedo is roughly around 0.85. Means what? 85% is reflected. When we talk about the floodplains or the grasslands, here the albedo marshy grasses. The albedo is in the range of 0.15 to zero point 0.2, which means 15 to 20% of solar rays are reflected. Is that understood now? Is that understood? What you write as 0.85, I write albedo as 0.85. What else can I write as 0.85? What I write as 0.5, I write albedo as 0.15. One of you were giving me the entire thing. Uh, Ankush, is that understood now? You had an entire logic developed why B will be cooler. Is it making sense or is it simply bouncing over? I hope it makes sense. Now, this factor of albedo is basically, this factor of albedo is one of the basic factors which influences temperature. The amount of solar rays reflected will also influence the amount of solar rays absorbed. How or what do I mean by that? Basically, let's suppose on this surface, if the albedo is 0.8, albedo varies between 0 and 1. 0 indicates complete absorption, 0 reflection. 1 indicates complete reflection and no absorption. Let's suppose the surface has an albedo of 0.8. So in this situation, if the solar rays, let's suppose 80% of it will be reflected, only 20% will be absorbed by the surface. Okay, let's consider another surface. Let's consider another surface. Now here, if it has got an albedo of 0.4, that means it is going to reflect 40% of the solar rays and 60% will be absorbed. Now, if I name this as A, if I name this as B, which will indicate a higher temperature, A or B, which will indicate a higher temperature? Very good. It will be B. Why? Because in B, 60% of the solar rays are held, they are absorbed. In the case of A, only 20% is absorbed, right? So that is why when you have snow covered areas, ice covered areas, I hope you would have seen when you go to when you go for skiing or when you observe the mountain expeditioners, they have a very thick uh, glasses, right? The sunglasses that they have. The sunglasses that they have, it is not for a fashion sense or a fashion statement that they are making. It is to prevent them from a kind of a solar glare, which will impact the eyes, which will damage the eyes, because that is the amount of solar rays getting reflected from the ice surface. Okay, that is why they have to put those glasses in order to protect their eyes. It helps them basically look at things normally without squinting their eyes. Okay, so it is most, that is also one of the reasons why in hotter areas always it is advised to paint your houses brighter from the outside. White paint is done from the outside. Why? Because the whitish paint from outside will reflect the solar rays. They will not trap the solar rays. Okay, as a cooling solution, many of the times what is done is that a flattish plaster of Paris is done and a white distemper is put. And in the older houses, you will still find it gets very warm because many of the portions have patches have blackened out, the paint has removed. So in those areas, there's a greater absorption. But if you have that plaster of Paris or that whitish distemper, so that will reflect the solar rays, keeping it cool inside. Okay, so this is a factor of reflection of solar rays, which does influence the temperature. At the same altitude, if you have hard rocks and if you have snow, so hard rocks will always end up attaining a higher temperature as compared to the snow region, because the snow will reflect more. Okay, let's suppose we consider Tibetan highlands at a height of 5 kilometers above the sea surface. In certain areas of Himalayas, let's suppose at a height of 5 kilometers, you might have snow covered areas. So, those snow covered areas of the Himalayas will be colder in comparison to the Tibetan plateau, because the Tibetan plateau is made up of the darkish, blackish basaltic rocks. And these basaltic rocks, because they are blackish in appearance, they get hot very quickly. Now, if ever you have visited, let's suppose, Taj Mahal, despite the warmest of the sun, you can still manage to walk barefoot there. Touch the outside of the Taj Mahal, it will still be cooler. Why? Because it is the whitish surface will reflect the sun, right? But try doing the same thing with the Red Fort or the Agra Fort. Now, it will be very hot. Why? Because there it will have a kind of a absorption, albedo will be lower, there will be greater absorption. So different areas have different amount and different quantities of albedo that they possess. It is not fixed. Okay, now for example, water is dark blue in appearance. It will always have a lower albedo, means it will reflect less, absorb more. When you absorb more heat, it will get warmer. The concrete buildings, the darker buildings that you have, the black roads that you have, they will absorb more amount of heat because of their property. That is why when you have the glass buildings, the reflective glass buildings, they manage to remain cooler on the inside because they are reflecting the solar rays. Very little amount of sunlight actually comes in. Okay, so that reflection of solar rays, if it is done ably well, then temperature can always be controlled. Is that understood? Is that one of the reasons why the Himalayas are always covered in snow, as not enough amount of heat is being absorbed? Along, one of the factors of lapse rate is also there. Lapse rate, basically with greater height, the temperature will always reduce. Having said that, the influence of albedo can now be observed in the region of Himalayas, because in the northern part of our country, we have significant amount of pollution caused because of population density, because of geographical factors, etc. Greater amount of pollution means you also have black carbon, excuse me, very tiny particles of black carbon which are emitted in the atmosphere. Now, much of that black carbon is carried by the factor of the wind, and that black carbon eventually can get deposited, and it does get deposited over the snow capped peaks of the Himalayan mountains. And that is when, imagine the Himalayan mountains, snow capped mountains, having these deposits of black carbon. Now, what will it do? In this patch, it will increase the amount of solar rays being absorbed. So here, there will be melting. If the ice thins out, the amount of solar rays that it can reflect will be very different than a thick whitish sheet of ice. Okay, so that black carbon deposits in the region of Himalayas is accelerating the glacial melt in the region of Himalayas. They are melting, exposing the lower layers of ice, exposing rocks in certain cases, The rocks being darker in appearance, etc., they absorb heat, and that is when they further lead to a continued melting process. Okay, so that is how albedo does influence, the factor of albedo does influence the rate of melting and heating also. Mountains are at higher altitude and thus lower amount of clouds and water vapor and thus reduces heat trap. No. What is albedo? Albedo is a surface phenomena. Albedo is not a phenomena of the amount of water vapor, amount of cloud cover. It is the nature of the surface. That's it. In this region, if I cover this entire region with snow, regardless of the atmospheric conditions around it, albedo will change. Right? So always remember, albedo is the surface phenomena. It is a surface phenomena. Nature of the surface. Absorbs or reflects the solar rays. Is that understood, Prem? Okay. In certain ancient temples, though made of dark colored rocks, seem to have cooler temperatures inside. So the dark colored rocks which are on the outside and in the inside, there is no sunlight, direct sunlight which comes through. So that is why it remains cooler. If you have for example, the Brihadeshwar temple, for example, in the Brihadeshwar temple, in that construction, by the time that you get to the inside the regions of the Garbh Griha, etc., you will never have direct rays of the sun ever reaching there. Right? The direct rays of the sun, they will fall on the top of the temple. That's it. So the inside of it manages to remain cooler. For example, if you are talking about the Kailash temple at the monolith temple, which is dark, made up of dark granitic rocks. Now there in the inside, there is no sunlight which ever reaches there. Let's suppose if you talk about the temple architecture, the Dravida temple architecture of the Aihole temple. Now, there in that kind of a temple architecture, if it would have been made up of a dark rock, it would have been superheated because the solar rays, they are able to penetrate through and through. Right. So, just because of the fact that in certain temples the solar rays they never come through, it remains cooler throughout the year. Okay. Now, this factor of albedo, this concept of albedo is also influential in accelerating the melting of the Arctic. Now, Arctic is one of those ice covered areas under which there is water, right? Now, here, I hope we are able to imagine the fact that this thin piece of ice will have lesser reflective power as compared to this thick sheet of ice, because it is more whiter, the nature is more solid, this is a bit more transparent, the thinner portion is a bit more transparent, and water here will absorb more, will reflect very less. So that albedo varies. So that is why the Arctic melting is also accelerated because of one of the factors is albedo. How? So in the region of Arctic, in the region of Arctic, in the region of Arctic, basically, here, melting is initiated. Why? Because of global warming. Due to global warming, melting is initiated. Now, once this melting is initiated, ice thins out and water is exposed. Thinner ice and water have ice and water have very low albedo. Means what? It means they absorb more solar rays. They absorb more solar rays. As they will absorb more solar rays, further heating occurs. As this further heating occurs, thereby, what will happen? Thick ice sheets start to thin. And melt. And thereby the cycle is repeated. So it is a consistent feedback loop in which the Arctic is stuck over, where the heating of the region of Arctic due to the global warming has induced some amount of melting of ice. Now, in those areas where the ice has actually melted, there is a greater absorption of solar rays in those areas. Greater absorption of solar rays means a higher temperature is experienced, and that further accelerates the rate of melting in other regions also. So this is observed not only in the region purely in the North Pole, but even, let's suppose, in the region around Greenland, in the region around to the northern portion of Europe. In those areas also, you will have the case that as the top layers of that permafrost, they are melting. So that is inducing a further accelerated melt, because the stones which get and the rocks which get exposed, they absorb greater amount of heat in the process. So that is the process of albedo. Now, from here, we come to one of the other basic concept, and that is the heating of land and water. So basically, how differently does a piece of land get heated up or cooled down as compared to a water body? That is something which we'll cover here. So let's suppose we consider a land area. Let's suppose. And by water from here on, in the entirety of our discussion, whenever we discuss a water body, let me specify, I'm not talking about the pond or a lake in your backyard or a river which flows near you, regardless of the fact that maybe in your local tradition, you might call that as a sea or the ocean of the world. Whatever might be the case, I'm not going to talk about the rivers, the lakes, and the ponds here. Whenever we talk about water bodies, we are going to talk about the oceans and seas. We basically mean the oceans and the seas of the world. Okay? I hope that is understood. Now, here, basically, let's suppose you have a water body. Okay. Now, the solar rays, they fall here also, they fall here also. Okay. Now, when the solar rays they fall on the land surface, on the ground surface, does it penetrate into the lower regions of the ground? No. All those solar rays, they are restricted to the top few centimeters of the ground itself. Over the land area, the solar rays, they are concentrated. Solar rays are concentrated. In the top few centimeters or a few inches of the ground. That's it. Maybe 3 centimeter, maybe 4 centimeter or 5 centimeter. That's it. Sunlight won't be able to penetrate on the ground surface. But when we talk about the water body, now in the case of the water body, the solar rays they will penetrate. They will penetrate to a depth of maybe 1 kilometer or 2 kilometers from the surface, isn't it? So the solar rays they will be penetrating. They will get distributed. Now, out of the water body and the land area, which will gain the temperature quickly? I'm not saying which will become colder or warmer, which will gain temperature quickly, the land area or the water body? Very good. Always the land area. Why? Because in the land area, the heat is concentrated on the surface. In the water body, that heat gets distributed, isn't it? In water body, in the water body, no, it is not the factor of albedo here. Body, the heat gets distributed. So as a result of that, more time is taken for rise and fall of temperature. Why albedo will not be a factor? Because let's suppose the water is bluish and the light blue, whereas the land may be made up of dark rocks. So that will that means water is more reflective there. So understand, just because of the fact that in the water body that heat is distributed along, right? Many of us might not be aware about the concept of specific heat. That is why I'm talking about in this kind of a language, that it might happen that the heat basically gets distributed along, because all those solar rays they will penetrate the water body to a depth of 1 kilometer or 2 kilometers from the surface. So that means greater time will be taken to indicate a rise of temperature by even 1 degree Celsius. Whereas over the land areas, all that heat is concentrated on the surface. That means that rise of temperature will be very quick. So that is where we come to the first conclusion. And the first conclusion is land gains heat much faster as compared to water. The land gains heat at a much faster rate as compared to water. It gets very hot very quickly. Now the night time. When the night time arrives, that is when it has to lose heat. Night time basically means that heat will be lost from the surface. Now, in the case of the land, the heat is concentrated only at the surface, whereas in the case of the water body, that heat has now distributed throughout the day. The water has gotten heated up, so that heat has gotten distributed over, isn't it? So, in the case of the land area, that loss of heat will be very fast because all that heat is on the surface itself. Whereas in the case of the water body, that loss of heat will take time because that heat has been distributed. So, that brings us to the second conclusion, that is, land loses heat much faster as compared to water. So land gains heat much faster as compared to water. Land loses heat much faster as compared to water. Comfortable up till here? Yes, Prem. That is correct. Comfortable? Okay. Now, from this, we come to a certain set of derived conclusions. One derived conclusion that we can come from is the fact that temperature during day. Now, land will gain heat much faster. That is why during day, land is warmer in comparison to water. Now, during night, it has to lose heat. So, during night, land is colder as compared to water because land cools down or loses heat much faster as compared to water. So, land is colder as compared to water. So during night time, that is why the in comparison to the land areas, the if you go to a coastal region, you will observe that the sea water or the oceanic water is slightly warmer because it takes time for that water to lose heat, and by that point of time, the land has already become cold. Okay, now then during the summer and the winter months, during summer, because when we talk about summer and winter, we are talking about prolonged exposure to sunlight during summer. On an average, for those 3 to 4 months, there's a greater exposure to solar rays, isn't it? During that entire month of summer, there's a greater exposure to solar rays. So here, land on an average remains much warmer as compared to water. And during winter, the reversal will happen. So when we say during winter, a reversal will happen. So that means winter means loss of heat. A prolonged duration of loss of heat will be experienced during winter. So in winter, you will experience that land on an average is colder as compared to the water body. Okay. So this basic factor of heating and cooling of land can influence the occurrence of rains in certain areas, can influence the movement of winds in certain areas, the occurrence of cyclones in certain areas, and so on and so forth. This particular, many of the concepts in climatology are driven from this basic aspect of heating and cooling property of land and water, that the land gains heat much faster, land loses heat at a much faster rate. So water takes time to become hot. Once it has become hot, it will take a large amount of time to become cold again. Okay. Now, after this, we move on to the portion of urban heat island. What is an urban heat island effect? So, when we say an urban heat island, here the term island is used. Now, island, what does it indicate? Island is a landmass in between the oceans from all sides, so there is a slight variation, right? Land is a slight aberration in the otherwise continuous water body. Similarly, when we talk about the urban areas, they indicate an anomaly in temperature. If you observe the temperature of an entire area, of an entire region, the urban pockets will indicate a sharp increase in temperature. So, these urban pockets where the temperature suddenly rises up, it is cooler in the surrounding areas, but in the urban pockets, the temperatures, when it suddenly rises up, and it does rise up because of various factors, that is known as the urban heat island. So, here, if you observe this particular image, basically, see, that is why I knew this kind of a question will come. During winter, we can't even touch water, and you are saying land is on an average colder. And smileys after that. So, again, when I say water, I don't mean to say the bucket in your washroom, which has not seen the light of the day, I don't know for how many centuries and millennia. Or when I say water, I don't mean the small pond in the back of your house, regardless of whether you call it Pacific Ocean, you call that small pond as Atlantic Ocean, whatever you call. I'm not talking about that small pond, that small lake. I'm not talking about the nearby river water which is flowing, that early in the morning I go to River Ganga to take a dip and it is very, very cold. I'm not even talking about that. I'm talking about the seas and the oceans of the world, because they have a major influence on the climate of the world. So, in comparison to the land areas, you will always find the water body during winter months to be warmer, because that water will retain heat. For, and again, don't compare it to the bucket in which you had stored water overnight and you have to take a bath next morning. Don't compare it to that. For example, in case you are having difficulty in imagining, for example, in the region of Northern Europe, you will find that the water is comparatively, the oceans are comparatively warmer, the land is easily frozen up. So, that kind of variation I'm talking about. Okay, I hope this is taken. Okay, now coming to the, okay, yes, another question which many of you ask: why in winter groundwater is warmer and in summer it is cooler? What do you think? Surprise me with some good answers. Act of God, Anything like that? Lava on the inside. Vibhu, very, very good. Beautiful. The question, GIB, was that basically why is it that in winter the groundwater is warmer, whereas in summer it is cooler? Very good, Vibhu. Parimal, very good. Isha, you are partially there. It is always the case that groundwater maintains the temperature. Groundwater has that consistent temperature because it is not in contact with the outside surface. So it is not impacted by the heating and cooling of the outside. So at that consistent temperature, maybe the temperature, let's suppose the temperature is 20 degrees Celsius of groundwater, 24 degrees. If the outside temperature of 40 degrees, when you pump out that groundwater, it will appear to be cooler. During the winter months, when the outside temperature is 8 or 9 degrees Celsius, you pump out that 20 degrees Celsius water, it will appear warmer. So groundwater is not impacted by the outside surface phenomena of temperature variation. That is why it maintains the. Having said that, if you have observed large wells, the open wells, now in those wells the water is exposed. So there will be slight variation. But let's suppose the hand pumps that are basically used, there you will find this impact where during the summer cooler water comes out, but that is again relative temperature. Okay, very good. Two of you had given the answer to the point, Vibhu and Parimal. Beautiful. Now, here we come to the urban heat island effect. So when we say an urban heat island effect, basically in the urban areas, you experience a sudden and a sharp rise in temperature. This is the curve. Let's suppose this indicates the temperature. So observe that in the rural areas, you would also have experienced it. If you have been fortunate enough to be born and brought up and the upbringing has happened in the rural areas, if you have been that fortunate, you would always have observed that it is always slightly cooler, right? The temperature conditions are always slightly cooler. But when you come to a township area, it gets slightly warmer. When you get to the urban landscape, it becomes very hot, right? Again, near the urban area, if you go to the rural area, slightly cooler. Why is that the case? So it is partially because of the factor of albedo, partially led by the other factors due to which the urban areas they experience that sudden sharp spike in temperature. So that factor is known as the urban heat island effect. Now the reasons for that urban heat island effect are manifold. First is that in the urban areas you have a large dominance of the concrete structures, the dark asphalt tarred roads, the the tarring that you do on the roofs, on the terraces in order to provide waterproofing. All of that will be absorbing the heat, will not be reflecting the heat at all, right? So that is why there is a greater temperature. So that means lower albedo and higher temperature. Shalja, because in winter upper layer of water is facing most colder. No, Shalja, that is incorrect, because when we say about groundwater, understand heating and cooling of the surface that we are talking about. Groundwater is present at 100 meters, maybe 100 feet deep or 100 meters deep. So it will not be impacted by the cooling from outside, heating from underneath. That will not be impacting the temperature of the groundwater. Okay. Now, the presence of darker surface in the form of asphalt, rooftops, etc. That means a higher average temperature. Now, in the urban landscape, you would have observed very close constructions. Very close constructions, buildings almost near each other, on top of each other. So there, when you have such kind of construction, there is almost negligible amount of scope for the wind movement, right? There's almost negligible scope for wind movement. Now, wind provides that cooling. So, if there is no such wind movement which is allowed in an area, so that means all that air, that heated air, gets trapped. And that is where it becomes very, very hot. For example, you would have come across this phenomena. I don't know how many of you have actually experienced this in your life, that if you come across a region where you have two buildings, there's nothing in front and behind it, but two buildings in close vicinity, very close vicinity, you will find a consistent wind motion in that area. You will find that breeze is, or the wind movement is very high. If the buildings are very close, there is no construction in front or no construction behind it, there's a kind of a rapid movement of wind in that area. You would have experienced that kind of a tunnel effect, but impacted by the Bernoulli's theorem. You would have experienced that. Yes. So, if let's suppose in that region you construct multiple buildings in front and behind it also, there will be no such motion. So, air gets trapped. So, that is where, because of the lack of movement of winds and lesser heat dissipation, this leads to higher temperature. Okay. Now, then lack of green cover. So even in urban areas, if you go to the regions where you have large gardens, for example, if you go to the regions where you have, let's suppose, a lot of trees, it will be cooler because the shade of the trees provide that cooling effect. Lack of green cover makes the region generally hotter and warmer. Then here also, greater greenhouse gas emission in the urban areas. Greater greenhouse gas emission means greater trapping of heat. Greater trapping of heat. Greater trapping of heat means higher temperature. Okay. Then greater heating due to electrical and cooling devices. In the urban area, the energy consumption is very, very high. Now, many of the office spaces, buildings, residential societies are such that even during the daytime, there is a requirement of air conditioning units to be perpetually running. Majority of the offices that you go to, even during the daytime, the air conditioning units will be functional. Now, these ACs, they create colder conditions inside, but their exhaust emits warmer air to the outside continuously. So, greater amount of this cooling device, greater amount of the electrical appliances and their utility, all of that generates its own share of heat, which increases the amount of heat observed in the urban areas. There is also one factor, that is lack of open soil regions. Here, we don't mean barren soil, but basically open spaces. In urban areas, you don't have many open spaces. So, this can also be translated into lack of open spaces. So, what is the factor of lack of open spaces? How will it influence the temperature? Understand. Let's suppose here you have an open space. Okay. Now, when the rain falls, let's suppose there's a rainfall. Now, this rainwater will percolate, will seep down ever so slowly, will get down ever so slowly, isn't it? Now, after this rainfall has abated, what will happen to this water, which has been trapped by the ground surface, etc.? Let's suppose the next day, all that starts to evaporate, water lost due to evaporation. water lost due to evaporation. Now, are we aware of the fact that evaporation causes cooling? Are we aware of the fact that whenever evaporation happens, the surface cools down? For example, when during the summer months you perspire, let's suppose you do a lot of physical activity and you start perspiring. Now, then, when you sit in front of the fan, you feel cooler. Why is it so? Is it because that fan is giving you colder air? No, the fan is simply circulating the air so that all that sweat, all that perspiration evaporates, and that provides that cooling. So evaporation always does provide significant amount of cooling. So here also, if you have open spaces, open soil regions in the rural areas, there is a greater amount of cooling caused due to that evaporation, right? But when we talk about the urban areas, any amount of water flow basically immediately is directed through the manholes and the sewage into the drains. Does not mean that we should have more open drains in the urban cities, etc. No, just more open areas in the urban environment that can cause significant natural cooling. So what can be the remedy of it, the solution? Better design and architectural setup for these buildings, right? For example, many of these buildings, what we refer to as the concept of green buildings. Again, I hope we are aware that green buildings do not refer to the fact that a building which is painted green. If you call that as a green building, that take a left next to the green building, that is a different matter altogether. But green buildings which are eco-friendly, where during the daytime enough sunshine comes through that you don't need artificial lights, where enough adequate airflow happens to keep the natural temperature cooler in the buildings, right? And for that, greater architectural designs have come into existence where natural flow of air is allowed. And here the architects are basically taking the inspiration from the ant hills. You observe the ant hills out there in the open, right? Very hot conditions these ant hills they persist, they exist. Now they inside temperature of these ant hills is cooler. Now, the purpose or the reason behind that is that in the anthills, you have so many small passages and so many small capillaries that the same effect is created that I told you that two buildings are in very close vicinity. There is nothing in front or behind that allows a rapid movement of air, right? So, that is how green buildings they help in not only reducing the energy consumption, reducing the greenhouse gas emission, but at the same time providing natural cooling. Also, the urban landscape should be dotted with green spaces. Here we mean trees and vegetation, which will provide natural cooling to that area, and open spaces will also be there. The distribution of population should be uniform so that all the population, all the construction is not concentrated only in one area. If you have a distribution, that means no such area will have a huge concentration of buildings. That means the buildings can be dispersed. That means there can be a natural variation in temperature also. Okay? Yes, Sushmit, that is correct. So that is the concept of urban heat islands, why they occur, and the remedy of them also. Right? Now, after this, we take a break. Green building area cover with plants in building from outside? No. Green building means eco-friendly buildings where the construction is such it allows the natural flow of air, it allows for natural light to come in. That is basically the green buildings, right? How do green areas stay cooler? Because they avoid that direct sunshine to heat up that region significantly. Shelja, don't worry. As long as you are understanding the concept, everything else works. Okay, so we take a break here, guys. We take a break of 15 minutes. I think that would be sufficient. Let's take a break of 15 minutes and let's be back in 15 minutes. A confirmation about the audio, please, guys. If the audio is clear, thank you. So, after this, we come to temperature and the variation in temperature. Now, we have seen about the variation in terms of insolation. Insolation is one of the factors which influences temperature received and experienced in an area. But there are a lot of other factors at play simultaneously, which influences the temperature experienced in any particular region. Now, whenever you, if ever you have witnessed the or listened to the news report, the weather report, you would have come across a factor of maximum temperature, minimum temperature. Maximum temperature is 25 degrees Celsius in Delhi, minimum temperature is 20 degrees Celsius, etc. You would have heard about that maximum and minimum temperature, right? I hope I'm not sounding like an alien language here. Okay. So, when is it that maximum temperature in a region is measured? Maximum and minimum temperature. When is it that a maximum temperature in a region is? Do we have any clue? Maximum temperature is generally measured at around roughly around 2 p.m. 2 to 3 p.m. That is when generally in the day you have the maximum temperature and minimum temperature, because that is when after that, after around 2 to 3 p.m., the intensity of the solar rays they start reducing and the heat gain starts to reduce. And you would also have heard about minimum temperature. So minimum temperature, when is it measured? It is measured roughly around 5 a.m. in the morning, because that is the extent till which the heat will be lost. After 5 a.m., 6 a.m. onwards, generally the sun starts to rise up and some amount of heat is gained by the ground. So this is the case. So the variation in the maximum and minimum temperature, that variation, this is also what is referred to as in temperature. This is also what is known as diurnal range of temperature. Generally, in common parlance, in layman's term, regarded as the temperature between the daytime and the night time, but more or less it reflects the variation in between the maximum and minimum temperature. Having said that, when we talk about temperature distribution, the region, when it experiences different types of temperature or different amount of temperature, it is dependent on a variety of factors. So what are the various factors which influences the temperature distribution? One of the first factor is the latitudinal extent of a place, because the latitudinal extent of the place basically influences the amount of solar insolation, the power of the solar rays, the angle that the solar rays they make with the ground surface. So the latitudinal variation influences the solar insolation, and that is a major factor in influencing the temperature in that area. That is why around the lower latitudes you will always find the temperature to be very high, because there you will have a greater duration of daytime also, and also the solar rays will be much more direct. So lower latitudes have, yes, Prem Kumar, correct. Lower latitudes on an average indicate a higher temperature Okay. Why? Due to direct rays of the sunlight, of the sun falling for a greater duration. That is why in the lower latitude, so here observe this. This particular image tells you that in the tropics, the temperature roughly on an average is 24 degrees Celsius above. On an average, it can reach 40 degree also, 45 degree also. But as you move into the temperate areas, it becomes slightly cooler. Move to the polar regions, the temperature goes into the negative territory. Minus 30, minus 20, minus 40 degrees Celsius, minus 50 degrees Celsius in certain instances. So the temperature, as you move away from the equator or as you move towards the higher latitude, there is a reduction in temperature. So higher latitudes indicate a lower temperature. Okay. Now, the other factor which influences the temperature is the altitude of a place. For example, if you consider Ooty, now Ooty and let's suppose Chennai, they are situated almost along the similar latitude, not much of a latitudinal variation. There is a couple of degrees of latitudinal variation, but not significant. But Chennai experiences a very different climatic condition. Ooty is much cooler. Why? Because of altitude. Similarly, with Agra and Darjeeling. Darjeeling and Agra almost at similar latitudes. But Darjeeling, you will find that the temperature on an average is around 4 degree, 5 degrees Celsius during the winter months. Agra is around 16, 17 degrees Celsius. Why? Because of the factor of environmental lapse rate or the positive lapse rate that we have talked about, that it becomes cooler as you go to a particular height. Why? Because on top of the mountain, the density of air is very, very less. So there is nothing to trap the heat, to retain the heat. So whatever amount of solar rays they fall, that heat is immediately lost because the air is very thin in that region. So that is why temperature decreases with height at an average of close to around 6.5 degrees Celsius of temperature drop per kilometer. Okay, so that is basically why with a greater height you have lower temperature, higher altitude, lower temperature. Lower temperature. Latitude and altitude are different, my dear friend. Latitude and altitude are not same. Latitude, and I hope none of us are getting confused between latitude and altitude. Are we confused in latitude and altitude also? Nikat, is there any confusion between latitude and altitude? Latitudinal position, when we talk about the planet has got various different latitudes. These are your latitudes. These are your latitudes. But at the same latitude, you can have a region at sea level, you can have a region at a higher level. Is that understood? Is that understood now? At the same latitude, a place can have a higher elevation, a place can be closer to the sea level. So here you will have lower temperature. Here there will be higher temperature. Positive lapse rate. We have discussed the concept of positive lapse rate. Yes, Prem. Then you have other couple of factors. One is the distance from the sea. In general, you will find that the coastal areas, they have a moderate temperature. Coastal areas will never experience extremities of temperature. A much great variation between the daytime temperature or nighttime temperature won't happen. For example, in Mumbai. Now, if you go to Mumbai even now, it will be warmer. The daytime temperature maybe is 30 degrees Celsius or 28 degrees Celsius. Nighttime temperature will be 25, 24 degrees Celsius. But if you go to Delhi, the daytime temperature can be 25, nighttime temperature can be 2 degrees Celsius. Right? So, regions across the coastline, regions across the coastline experience moderate temperatures. They end up experiencing a kind of a moderate temperature. Why is it so? So there are a couple of factors. First factor is that, or let me elaborate this also, variation between day and night temperature or summer and winter temperature is not very much. Okay. So variation between the day and night temperature or the summer and winter temperature is not very high. Whereas in the continental areas or the inland areas, such as let's suppose Chandigarh, Delhi, Lucknow, Patna, Varanasi, let's suppose Amritsar, Ambala, Jalandhar, all those areas which are very far away from the coastline, you will find extremity of temperature. So there are a couple of reasons for them. What are the reasons? So the reasons for them, first of all, in the coastal area, we will study in the next module, there is frequent wind movement from sea to the land and land to the sea, what is also regarded as the land and the sea breeze. So that ends up carrying away any extremity of heat buildup or very cold conditions building up, because we know that there is a thermal difference in terms of heating of land and water. So even if the land becomes very cold, water will remain comparatively warmer. Even if the land becomes very hot, water will remain comparatively cooler. So there is a regular exchange of wind movement in the in between the land and the water body, due to which there is a moderation in temperature. So here basically you will have frequent due to the thermal difference between land and sea, consistent movement of wind, land and sea breeze. We'll study about land and sea breeze in detail in the next module. Moderates the temperature. It moderates the temperature. Whereas in the internal areas, in the continental areas, you don't have any of these factors at play. That is why the temperature remains or goes to an extremity. For example, if you consider the region around Britain or the Western Europe, now this region of Western Europe frequently experiences, which is on the coastline of Atlantic, it frequently experiences those maritime winds which come over. That moderates the temperature. At the same latitude, if you go to Russia, in the region of Siberia, you will have very cold conditions because there is no such moderating impact. Okay, so the influence of water bodies is quite significant here. The other factor is coastal areas have higher humidity. Higher humidity, so what? Can you think of a logic why higher humidity means a consistent temperature? Can we think about a logic from here? Don't be afraid to take a guess. Beautiful. Across the coastline or a few, as long as the maritime effect or the winds are marine winds are able to come, Ankit, that is the coastal area. It may be few kilometers, it may be few 100 meters. Many of you are correct here. No, Isha, incorrect. Higher humidity automatically means more water vapor. Higher humidity, that is not the solution that higher humidity means more water vapor. Why more water vapor means moderate temperature? That is the question. Good. Amritansh, Ankush, all of you correct. No. Salinity has got nothing to do with it. See, don't be sorry. Please don't say sorry if you have said an incorrect answer. Please, please. I want you to take a guess. I want you to commit mistakes here itself because the more that you think about it, that is where the muscle is put to use. So don't be afraid to take a random guess because the winds come from the oceanic areas. Yes, good. So when you have higher humidity or higher moisture content, basically what it means is there will be a greater trapping of heat. So heat won't be lost very easily. When is it that the nighttime temperatures become very low? When the heat is lost with a very great amount of pace, that is when the nighttime temperatures they become extraordinarily low, isn't it? So here, higher humidity means greater retention of heat. That greater retention of heat means overall average temperature is consistent. Okay, so that is why in the coastal areas, because of these two reasons, you will find that the daytime nighttime temperature is almost constant. The winter summer temperature is almost constant, right? What is also known as the maritime temperature, where you will have rains also happening very frequently. No extremity of summer or winter will be experienced in those particular areas. So that is why the region, for example, Mumbai, Goa, let's suppose if you talk about Kochi, Trivandrum, Chennai, Vishakhapatnam, Puri, Kolkata, all of them, they end up indicating a kind of a moderation of temperature. Whereas if you talk about, let's suppose, the region of Nagpur, extremity of temperature a bit. Churu in Rajasthan, extremity of temperature. Jaisalmer, extremity of temperature. Delhi, extremity of temperature. In Delhi, the summer season can have you witness a temperature of even 45, 48 degrees Celsius. Winter, during these times, the minimum temperature oftentimes can reduce to around 2 degrees Celsius. So there is that variation. Okay. Then other factor is basically the case of prevailing winds. Here in Udaipur, Rajasthan, it's winter. Yes. In the entirety of India right now, it is winter. And in daytime, we get copious amount of heat on land. Still, why it feels cold in the afternoon? See, you are getting that heat, but overall understand that as of this point of time, the solar rays that you are getting, they are already at an inclination. The solar rays that you are getting right now, they are not the direct rays, because the northern hemisphere right now is tilted away from the sun. So think about it, that sun, the solar rays right now are vertical over the tropic of Capricorn. Now, during the summer season, when the tilt is such that, let's suppose the sun is here and direct rays are coming in, so they will cover a shorter distance to reach your place. And that is why you will basically feel a much greater amount of heat during the summer. But during the winter, you get that slanting rays of the sun. That is why it is not as powerful. Now, during the summer months in the afternoon, you will feel very hot. During these months, you feel cooler. Why? Because of that. Okay. I didn't understand eject cause of higher humidity. Eject. Exact. You mean exact? Okay. So see, higher humidity. Why? What is humidity? The amount of moisture content in the air is humidity. Now, in the coastal areas, because you have the large sea or ocean body, so there will always be that consistent evaporation. That is why it will always be humid. If you ever go to the coastal area or the coastline, you will always feel the scenario where consistently you will be sweating or perspiring, and that sweat won't evaporate from your skin. And that is because of the fact that you have the situation where outside or around you the air is already having so much amount of moisture because of the supply of moisture from sea or ocean. That is why. Okay, two or three of you have asked the same question, and the question is probably revolving around why am I wearing half sleeves? And is it the case that Bangalore is not experiencing winter right now? Bangalore is also experiencing winter, but not to the extent that Delhi is experiencing the winter, right? Or the northern part of the country is experiencing winter. It is of a different range altogether. So, if let's suppose if you have been living in this area or Bangalore or the southern part of the country in general, to the south of Tropic of Cancer, there you will never experience the temperature to go below 10 degrees Celsius or so on. The temperature will always be slightly higher. Okay. Whereas when you talk about the northern part of the country, the temperature dips quite significantly. It is a different matter altogether that even in a temperature of 20, 22 degrees Celsius or 18 degrees Celsius, in areas of Mumbai, you will have people wearing jackets and having that bonfire lit up and warming themselves. But if you have been an individual who is very used to the winters of the north, the winters of south, they are very, very moderate. That is the diversity, the climatic diversity of the country, which when we come to Indian geography, you will be able to appreciate it much more. Okay. And then is there, so the entire country is experiencing winter season, but again, the temperature is different. Is moisture retains the same temperature? Moisture retains heat. Githyon. So it doesn't allow the heat to escape. See, the ground surface, when will it become very cold? When it will continue to lose heat profusely and continuously. But if there's a moisture cover which retains that heat, so that heat will be maintained. Okay. And Sushmit, downwelling regions are located along the boundaries where. No. Downwelling, upwelling, they are. Uh, is it something that you are downwelling, upwelling? You are referring to the oceanic downwelling, upwelling, or you are talking about the mantle movement of downwelling, upwelling? Because downwelling and upwelling is dependent on, in the oceans, they are dependent on the wind pattern. It is not associated with the plate boundaries. Okay, the tectonic movement. So ask me after the class. We will talk about that after the class. And coastal areas only have the regulated temperature. Yes, that is correct. Prem Kumar, maybe because Bangalore is slightly away of cold waves coming from Siberian high. The cold waves coming from Siberian high, my dear friend, does not even impact the northern part of the country. If the cold waves coming from Siberian high would have had a real impact in the northern part of the country, northern portion of the country would have been frozen. The region of Uttar Pradesh, Bihar, West Bengal, all of them, Delhi, would be covered under thick blankets of snow as of now. But because of the presence of Himalayas, you are not impacted by the cold Siberian wave. Okay, the Himalayas blocks them. Okay, now coming to the prevailing winds. Prevailing winds here refer to the existent wind patterns at any particular place at any particular time. So existent wind patterns. So here we are talking about the permanent and the local winds. For example, westerlies, which we study in the next module, that is the trade winds, westerlies, etc. Now, here we have already seen that you have cold advection as well as warm advection. When colder winds they come into the warmer area, they will cool down that region. When warmer winds come into the colder area, they will warm that region. For example, right now in the northern part of the country, you have an event which we will study later in Indian climate, that is the western disturbance. Now, that brings about snowfall in the region of the Himalayas. Now, whenever that happens, the region of Jammu Kashmir, Himachal Pradesh, Uttarakhand, whenever they receive fresh snowfall, cold winds from there, they start moving over the region of the northern plains. And the northern plains become very, very cold, right? So, even for example, in the northwestern part or to the northwestern direction of the country, in the region of Pakistan, you have the Potwar Plateau. Now, that Potwar Plateau starts becoming very cold from the month of October and in the initial part of November. Now, that starts driving winds towards the region of northern India. And that is when the northern India starts getting the grip of the cold waves. Right now, northern part of the country, you would have experienced that suddenly there is the temperature is maintained and suddenly it gets very low. All of a sudden, maybe one day or the other, it becomes very cold. And that is because of the fact of the very ultra cold winds getting supplied from the Himalayas because of snowfall carried by the western disturbances. Similarly, during the summer season, the temperature rises up when you have the influence of Lu, right? The influence of Lu. As this Lu basically moves, that from west to east direction, it raises the temperature in the northern part of the country. So, cold and warm advection will also influence the temperature. So, here basically, cold and warm advection, warm advection creates a variation in temperature. Ends up creating a kind of a significant variation in terms of temperature experienced. Okay. Now, there is another factor which influences the temperature, and that is the factor of ocean currents. Now, I understand that we have not covered ocean currents right now. We will cover it in very significant detail in the portion of oceanography. I understand we have not gained an idea about ocean currents. So, what are these ocean currents? Very briefly, I will tell you. It is not for your understanding right now. This is just a brief coverage of it. In the oceans, the oceanic waters, they move in a certain direction. Regardless of our popular perception that the oceanic waters are stagnant and oceanic waters they remain calm and stable, oceanic waters are in consistent and perpetual motion. Consistently in a certain direction, they carry millions of gallons of water on a daily basis, on an hourly basis. Now, these waters can be carried from lower latitude to higher latitude, means warmer waters are being carried to the higher latitudes, or these waters can move from higher latitudes to lower latitudes. That is, colder waters are being brought about in the lower latitude region. So, if let's suppose this oceanic current is bringing water from the region around equator or tropics to the region of higher latitudes, it is a warm oceanic water that it is bringing about. That warm oceanic water, when it reaches the region of the higher latitude, it warms up that area ever so slightly. It maintains or keeps that region ice free for most of the year. Similarly, when you have a cold ocean current, that means it brings colder waters from higher latitude to the region of the tropics or equator. Just like the advection is about the movement of the wind, here you have the movement of oceanic water. So, colder oceanic current means colder oceanic water being brought from higher to lower latitude. That will cool down the region, right? So that also has got an influence on temperature. So presence of warm and cold ocean currents. So warm ocean currents, for example, observe this one. These warm ocean currents, they will carry warmer waters up till the higher latitudes, and there they keep the conditions a bit warmer. Okay, but here you observe the cold ocean currents like the California current, the Canary current, the Venezuela current, the Peru current. They will bring colder waters from higher latitude to the lower latitude. And when they do so, they will cool down the area, they will cool down the region in this particular area. So that is why they will influence the temperature. So warm ocean currents increase the temperature of a region. Cold ocean currents reduce the temperature of a region. These happen in vertical or horizontal. These happen horizontally. There's a kind of a vertical circulation also. We will study in the portion of oceanography. But as of now, this is the horizontal variation. Shelja in India map, if we move towards UP to Jammu, we will face less temperature. Yes. And Megha, this phenomena only occurs in ocean. Why? What? The ocean currents? How will you experience ocean currents on land, my dear friend? Ocean currents will be in ocean. That is why the name ocean. Or are you asking that why not in the rivers or lakes or ponds? Is that what you are asking? Is that the crux of the question? Okay, because there are many factors at play for the generation of the ocean currents. It is one of the favorite areas of UPSC, why ocean currents are created. Rivers or seas are very, very small amount of water. So there you don't have that requirement or that generation of different temperature variation in different parts which can influence the flow pattern. Once you study about the ocean currents in detail, you will understand. And understand rivers and lakes, they are almost inconsequential in terms of the total water present. Just to give you a overall proportion, across the world, 97.5% of the water across the world is oceanic or salty and saline water, which is present in the ocean and the seas. Only 2.5% of the water of the planet is fresh water. Only 2.5%. Okay. Now, out of that, 70% of that fresh water is in ice and frozen condition, the glaciers and the ice. 70%, almost 69.5, is trapped in this region. Right, let me write it down, 69.5. Otherwise, I know the kind of a question which will be asked from you will ask from this. So 69.5 almost is trapped in ice and glaciers. 30% of that fresh water is trapped in the underground region. That is the groundwater. Remaining 0.4%, that is 0.4% of the fresh water. This includes all the rivers, all the major rivers that you know of, the lakes, the ponds, the water vapor in the atmosphere, all of them. They are inclusive only in this 0.4%. So that tells you that of that entire global distribution of water, rivers and lakes, how inconsequential they are. Right. But nonetheless, when we come to the portion of oceanography, when you study about the thermal factors within the ocean, you'll be able to appreciate it better why there is generation of ocean currents. 30% in groundwater. Githya, is it always moves in the same direction, even in any case of natural calamities such as no, oceanic convergence, divergence of plates, everything that is happening at the ocean bottom. These ocean currents, the horizontal ocean currents, they are the surface currents. They exist only up till the depth of around 400 meters from the surface. Ocean is around 5 to 6 kilometers deep, right, from the surface. So all these ocean currents, they are surface phenomena. Other than the northern Indian Ocean, it is here that the ocean currents, they change their direction, but in rest of them, the ocean currents are consistent. Now, then we come to the factor of isotherms. What are isotherms? So basically, if you have to indicate variation in temperature or the global distribution of temperature, how will you do that? Is it the case that on the map you will pinpoint each and every district, you will write the temperature next to it? Obviously not. So, in order to express that distribution of temperature or variation in temperature across the globe from one season to another, from one place to another, you use isotherms. These are imaginary lines which join the places indicating equal temperature. Hence the name iso and therm. Right? Iso and therm. Iso means similar. Iso means similar. Therm here represents temperature. So the line joining places of similar or the same temperature, that is what is regarded as an isotherm. Okay, that is what we regard as an isotherm. So here, for example, let's suppose you have an isotherm of 30 degrees, or rather than this, let's suppose you have few places. A indicating 30 degrees Celsius. Let's say B indicating 30 degrees Celsius. Let's suppose C indicating 30 degrees Celsius. Let's suppose D indicating 32 degrees Celsius. E indicating 30 degrees Celsius. So the 30-degree isotherm will have a movement or will be drawn somewhat like this. This will also be regarded as the 30-degree C isotherm. Okay, that is what is regarded as the 30-degree isotherm. So all the places which will lie on that isotherm, basically when you draw that isotherm, you will draw it joining all the places indicating 30 degrees Celsius. So conversely, we can also say that all the places on that 30 degree C isotherm will be indicating a temperature of 30 degrees Celsius. Okay. Now, these isotherms help us study about the variation in temperature. Now, a basic question. Can we have these isotherms crisscrossing each other? Yes or no? Under what conditions will they cross each other? If they will. So isotherms can never crisscross each other. Never. Isotherms, isobars, they will never crisscross each other. Why? Because let's suppose this is a 30 degree Celsius isotherm. Let's suppose this is a 29 degree Celsius isotherm. Right. Now, any place on that 30 degree Celsius isotherm will represent 30 degrees Celsius. Any place on the 29 degree isotherm will represent 29 degrees Celsius. But what about this place? What will be the temperature of this place A? Will it be 30 or will it be 29? What will be the temperature here? So that is why a place at the same time cannot indicate two temperatures simultaneously. That is why isotherms will never crisscross each other. So that is why isotherms will never crisscross each other. Even half a degree is considered. Don't think 1 degree is very less, my dear friends. I will tell you an anecdote here. I hope you try to appreciate it. You know, how do we predict the monsoons? We predict the monsoons by various different events happen across the globe. Heating of the Pacific, Atlantic, everything is taken into consideration. The oceanic temperature of Indian Ocean around equator, in Somali coastline, in the Indonesian coastline, the temperature of Tibet, everything is considered, and then it is fed into the supercomputer and it churns out the data, and eventually it gives you the prediction that monsoon rains are going to be normal, above normal, below normal, how much above normal, how much below normal. Now, in one of the years, the prediction which was made by meteorological department was the fact that this year it is going to be very dry. But it rained quite significantly. In fact, it had an excess rainfall, excess monsoon, rather than dry. When investigation was carried out that why did we have such a wrong prediction, it was found out that while feeding the temperature of different places, in the region of Arctic, there was a variation of 0.004 degrees Celsius. That variation was done while entering the data. So that had an impact in the overall calculation about the wind direction, etc., which could make the difference. So 1 degree Celsius is a very substantial one. We will study about the Indian Ocean dipole later on. Even a temperature difference of zero point 0.3 to zero point 0.2 degrees Celsius in the Indian Ocean between the region of Somalia and the Indonesian region, even a temperature difference of zero point 0.2 degrees Celsius can initiate an atmospheric circulation, which can bring rains in Indonesia or which can bring rains in the region of Somalia, which can influence Indian monsoon, which can increase Indian monsoon or reduce it. So 1 degree Celsius is quite a very high temperature difference. Okay. So isotherms basically cannot crisscross each other. Isobars, any of these cannot cross each other because of the reason that the same place cannot indicate two temperatures at the same time. How the temperature is chosen as it changes from time to time. So you have the maximum temperature or the minimum temperature. If you are measuring the isotherm across the minimum temperature, you will all note the minimum temperature of that area. Okay, right? But we can't get the same temperature throughout a day, never. Obviously, you cannot get the same temperature throughout a day. Obviously, that is the case. But do you think that, or for example, let's suppose at 2 p.m., the temperature is different as compared to 1 p.m. But so is the case everywhere. So if you are drawing an isotherm of at 2 p.m., isotherm at 1 p.m. will be different from that. So that is why isotherm is not something which is fixed out there somewhere in the world that, okay, this place has to have 30 degrees Celsius only because there's an isotherm passing. No, these are imaginary lines. It changes. The isothermal variation happens between the summer, winter, etc. It does happen. So that is why minimum, maximum temperature is taken, average temperature is considered. You have the summer isotherm, winter isotherm, etc. For example, this is the isotherm for the month of January. Now, for the entirety of the month of January, this is the isothermal representation. So, obviously, average temperature for the month of January is considered here. Now, January basically means it is winter in the northern hemisphere, it is summer in the southern hemisphere. Now, observe these isotherms, and here we will also observe the fact that how we have discussed in the winter water bodies are warmer as compared to the land at the same latitude. Land is colder in winter. We have seen that. Observe this thing with the help of the isotherms. But before that, first of all, in the southern hemisphere, it is summer in the month of January. So here, basically observe the isotherms in the southern hemisphere are almost parallel to each other. Why is it the case? In the northern hemisphere, the isotherms are haphazard, thrown up all over the place. But in the southern hemisphere, they are parallel to each other. Why? Because southern hemisphere is dominated by water body. And dominated by water body means there's a uniform distribution of temperature, uniform loss or gain of heat. So that is why there's, because of that uniform distribution of temperature, you will observe that there is a kind of a very uniform variation of temperature from one region to another. There is no such sudden change in temperature experienced. That is why the isotherms are parallel to each other. So here, domination by the water body in the southern hemisphere means the isotherms are parallel. Now observe the isotherms in the northern hemisphere. Now observe, this is the 0 degree C isotherm, 10 degree C isotherm, minus 12.5 degree C isotherm, minus 25 degrees Celsius isotherm. Now let us observe the factor of temperature variation between the land and the water body. So if I talk about this area, let's suppose Let's suppose I consider this latitude and I consider the temperature of different places on this latitude A, B, let's suppose A and B itself we consider. Now, what is the temperature at A? Let me know. Temperature at A by looking at the image. Let me know. Very good. -2. The best answer I have got is the temperature is low. That is the best answer by far. I know it is a low temperature, but can we decipher what is that low temperature, my dear friend? A here lies across this particular isotherm, -12.5 degrees. So temperature at A is -12.5 degrees Celsius. The temperature at B is 0 degrees Celsius. If I take a place here, let's suppose there, C, almost closer to around 10 degrees Celsius. Almost. Not exactly 10 degrees, but almost would be 8, 9 degrees somewhere to that range. So at the same latitude, A is -12.5, B is 0, right? And C is almost 10 degrees. So what does that tell you? That during the winters, land is very cold, water is a bit warmer. So if this region, if you are drawing an isotherm across this area, right, that is -12.5 degree, it will join all the places having -12.5 degrees. Fair enough. If you are drawing that isotherm, it will join the places of -12.5. But in order to attain -12.5 over water, you will have to move towards the region of the poles, almost in the region of Svalbard and Arctic. That is where you experience -12.5. If you are drawing an isotherm of around 0 degrees Celsius, observe, joining the places on land indicating 0 degrees Celsius. But to experience 0 degrees Celsius on water, you will have to move towards the region of the poles, isn't it? Because water at the same latitude is much warmer. So that is what brings us to the fact that during winter months, winter months, isotherms as they cross from land to water bend towards poles. Why? Because it is the fact that to attain that similar low temperature, you have to go to the polar area, because at the same latitude, water will be much warmer. Observe this condition. Over the land areas, observe, this is a thermal image. Observe that land is much colder, water is significantly warmer here. Okay, land is much colder. Now, southern hemisphere is experiencing summer season. There is almost a uniform variation of temperature, almost parallel to the latitudes. Why? Because it is dominated by water bodies. So there's a uniform distribution of temperature. In the month of July, when it is summer in the northern hemisphere, land will get much more heated up. So you will observe that the land areas, they are the ones which are significantly more heated up. Water is comparatively cooler. So in this case, for the Land is much hotter here. Let me write it down. During summer, land is much hotter. So, by application of a similar logic, if we draw an isotherm from land to water, isotherms, as they cross from land to water, they will bend in which direction? Pole towards equator, or they will not have any bend. What do you think? Cross from land to water, bend equatorwards. No, isotherms and isobars are different. GIB Canada experiences minus 20 degrees, but also isothermal temperature shows 0 degrees. So, Canada experiences minus 25 degrees also. In fact, northern portion of Canada will experience minus 30 degrees Celsius also. Is it the case that one country will experience only one temperature? In India, right now, let's suppose if we talk about Chennai, it is experiencing around 25, 27 degrees Celsius. But if we talk about, let's suppose, Ladakh, some portions are experiencing negative temperature also. So, is that the case that the temperature basically is going to be consistent throughout the country? Absolutely not. Okay. Prem Kumar. If in India we take temperature at 2 p.m., then in case of any other place in the world, do we require to take the temperature at the same time as per the time zone? No. The temperature at that point, on an average, you consider. For example, let's suppose what is the maximum temperature that they have experienced during the day. So 2 p.m., let's suppose 2 p.m. of Pakistan, 2 p.m. of India, 2 p.m. of Bangladesh, 2 p.m. of Myanmar. So you will have the maximum temperature isotherm. Like that, you draw. Okay. And yes, Mega, that is correct. Why are some isotherms in circular loops? Because that region in the entirety, it can happen that this region also 30 degrees, this region also 30 degrees, this region also 30, this region also 30, this region also 30. So you will have a loop. Okay. Some people will ask in that, is it possible one time whole fresh water will be destroyed? There is always that perception that all the fresh water will vanish. It might happen that the ice will melt in some area or the other. Some region will have the ice nonetheless, and rainfall will continue to provide water. Water cycle is consistent enough. Very rarely has the planet gone through a condition where there is no fresh water, because the groundwater keeps on supplying that fresh water from some watering holes, some ponds, some lakes in some area or the other. Kindly tell me how the temperature of different areas are measured and who receives these. Is it IMD? So you have local observatory stations, Jyoti, and you have an air thermometer. That air thermometer is suspended around 2 meters, 1.75 to 2 meters from the ground surface. In fact, I also had the image of that thermometer. What you observe here, this is an air thermometer. It is so this is a small weather station. So this basically the thermometer is suspended up around 1.75 to 2 meters above the ground surface, so that it doesn't get influenced by the ground temperature. This is the case of a rain gauge, which measures the amount of rainfall. Okay, this is your anemometer, which measures the wind direction in a particular area. how quickly that spins, what is the direction of the wind movement, that is measured. So you have these local weather observatories which continue to measure these data pointers. That is a consistent measurement. Okay, right? Now, after this, we come to the condition of temperature inversion. What is this temperature inversion? So, first of all, we do know we are talking about the region of troposphere itself. Tropospheric temperature inversion. So, what is this? So, here basically we do know that in troposphere you have a positive lapse rate. Positive lapse rate means what? Temperature reduces with height. Reduces with height. What does that mean? So let's suppose this is the ground surface. Near the ground surface, you have a higher temperature. Let's suppose the temperature of the ground surface is 25 degrees Celsius. So the air immediately in contact with the ground surface will also be 25 degrees Celsius or 24 degrees Celsius, let's suppose. Let's suppose it is not a perfect transmission of heat. As you move higher up, the temperature will reduce. It becomes, let's suppose, 18 degrees Celsius. Above it, it becomes 8 degrees Celsius. Like that, the temperature continues to reduce. 2 degrees Celsius, like that. Now, if I ask you, when you consider any air parcel or air sample, now, from this part to this part, is it going to transmit heat very effectively? Is it going to be a good conductor of heat? Or is it going to be a bad conductor of heat? Air, is it a good conductor of heat? Or is air a bad conductor of heat? Doesn't allow the movement of heat to be fast. Air is a very bad conductor of heat. Because of the gaseous molecules, it does not allow the heat to be or the energy to be effectively transmitted. So always remember that. So that is the basic logic behind the functioning of air circuit breakers, etc., that you would have come across. But nonetheless, so air is a bad conductor of heat. Of heat doesn't allow the heat to, for example, all the blankets, etc., that you wear or that you in these months, right? All the thick jackets that you have. Now, those jackets and those blankets, are they pure solid or are they puffy? You will find that the more puffed up cotton, etc., which is kept there, warmer the blanket is. Why? Is it the case that the cotton is providing you that heat? Take all that cotton out from the blanket and wrap it around yourself. You will feel very cold. Take all the cotton out from your jacket and wrap it around yourself. You will feel very cold. Basically, these jackets, these blankets, they trap the air between them. And the body heat is not allowed to escape through the air. That is why it retains heat. Your body retains heat and you feel warmer. Okay, so always air which is trapped, always it is going to be a very bad conductor of heat. It doesn't allow the loss of heat or the gaining of heat to happen very easily. Now, having said that, let's suppose certain climatic conditions happen in such a way that ground surface temperature or ground becomes very cold. Ground becomes very cold. So if the ground becomes very cold, the air in contact here, this place, this will, because it is in contact, it will also become very cold. But what about the air in this position? Is it in contact with the ground surface? No. So will it become equally cold in that case? No. It might maintain a temperature of 15, 18 degrees Celsius, whatever was there. So in certain conditions, during certain seasons and in certain regions, you will come across the condition that due to the climatic events, the ground surface or the air near the ground surface becomes colder as compared to the air above. So you have warmer air above, and colder air below. So this indicates what? A negative lapse rate. Negative lapse rate. That negative lapse rate is basically indicative of temperature inversion. That it is an inversion of the normal conditions. That is the temperature inversion. Now, in the earlier situation, you had the warmer air at the bottom. Warmer air always has got the tendency to rise up. Colder air always has got the tendency to sink down. That is always the case where the warmer air will tend to rise up, colder air will tend to sink down. But in this case, warmer air is already at top, colder air is already at bottom. So in the first case, you might have the vertical mixing of air, which will still happen. But in the second case, you will have the air which will be stable, which will not move. So that is the reason why during the winter months, particularly in the northern plains, when it becomes very cold on the ground surface, you have colder air near the ground surface, warmer air above. So the air doesn't mix. So the impact of pollution is much more exaggerated because the pollutants, they will stay in that colder air. They won't rise up. Here in the summer season, the pollutants could rise up, could mix easily. But in the winter season, you won't have that condition anymore. So that is why right now, for example, the impact of pollution that you witness in the northern part of the country will be much more exaggerated as compared to the other condition. So that is the case of temperature inversion. So temperature inversion is the inversion of the normal condition of the lapse rate. So in the case of, let's suppose, winter months or certain other conditions, there is a factor of temperature inversion which is observed, where you have warmer air which is trapped, and that is when the colder air is at the bottom. And why it happens, where it happens, on that basis you have the classification of temperature inversion into various types. So you have the variation of inversion classification into surface inversion, subsidence inversion, frontal inversion, these are the basic types that we are talking about, sufficient for your GS. Valley inversion. So whenever you have a condition of inversion, the colder air, which is already at bottom, colder air is the heavier one. Heavier air will not have the tendency to rise up. Warmer air has a tendency to rise up. Heavier air will always have a tendency to sink down. Here it is already at the bottom portion. Where will it sink down? Will it start carving out a hole for itself? So there is no mixing of air. No mixing of air. Prishika, I hope that is understood now. Okay. Now, the reversal of the normal behavior of temperature in the troposphere is known as temperature inversion. It is quite common, but it happens for short duration. It happens in various areas. For example, in India, we experience only these two kinds of inversion. Okay, so it varies from one region to another as well. An ideal situation for inversion is still air, that is lack of wind movement, long winter nights and cleared sky, because it is in these conditions, the ground loses heat very quickly and becomes very cold. And when the ground becomes very cold, air in contact also becomes very cold. But the air above, higher up, that is not getting impacted at the same rate. So the air above will continue to remain warmer overall. So that is why you have the inversion. So let us take a look at this. Why this inversion happens, where this inversion happens. So starting with the surface inversion. Surface inversion. The name in itself is self-descriptive. That this inversion is caused because of the event happening at the surface. Okay, this inversion is caused due to extraordinary drop in temperature of the surface. For example, let's take the case of Delhi itself. Let's suppose we take the case of Delhi. Now here, let's consider different scenarios. Let's consider a scenario at 4 p.m. and let's consider a scenario at 4 a.m. in the morning when it is going to be very cold. Now 4 p.m., the ground temperature, let's assume, is 17 degrees Celsius. Let's assume. Now the air in contact with the ground will also be colder or will also indicate somewhere around 17 degrees Celsius. Let's suppose the air in contact is also 17. Let's assume. All this is just for an assumption's sake to help you understand. Now let's suppose above this, at a particular height, the temperature is 10 degrees Celsius. Let's suppose above it 8 degrees Celsius or 6 degrees Celsius. Now, at 4 a.m., that is during night time, the surface will be losing heat almost continuously. The surface will be losing heat continuously. So the surface will become very cold. Nighttime temperatures right now in Delhi, what is the trend of nighttime temperature? Those of you from that area, living in that area, 2 degrees Celsius, 5 degrees Celsius, roughly around that. Let's assume 2 degrees Celsius. It will get to 2 degrees Celsius within a week. It can, unless and until there is a disturbance. So let's suppose that it is nighttime temperature gets to 2 degrees. The air immediately in contact will also indicate 2 degrees. Fair enough. Why will the air here from 17 degrees Celsius has come to 2 degrees Celsius? Because the land has cooled down. The land has lost heat due to the terrestrial radiation. The land has lost heat continuously. It has reduced to 2 degrees Celsius. So the air which is in contact with the land will also be at 2 degrees Celsius. Comfortable up till this, right? Now, what about this place? Will it also cool down at the same rate? It will cool down, but will it cool down at the same rate? No. From 10 degrees Celsius, maybe it has cooled down to around 4 degrees Celsius. But what do you have in this case? You have a warmer air here, warmer air, and here you have a colder air. So this is a negative lapse rate, a condition of inversion. But this inversion has happened. Why? Because the ground surface had cooled down during the winter month. Long winter night, clear sky means there was continuous loss of heat, right? So the ground surface cooled down quite substantially and sufficiently. So that is why you had the case where the air closest to the ground surface or in contact with the ground surface also cooled down. So that is why it is surface inversion. So when we talk about surface inversion, it occurs when the atmosphere at the Earth's surface is colder than the layer above it. Around sunset, the ground cools rapidly by radiating heat upwards into the space. Now, the air in contact with the ground cools by conduction, causing the lowest layer to be the colder one. Now, this is something that we observe in the various different parts of the country. And this is a temporary phenomena. Next morning, again, when the sun starts shining, the ground will heat up. The conditions of inversion will be reverted. Okay, so it is a very temporary phenomena experienced in India. Majority of the parts which experience inversion, they experience the surface inversion. However, in the mid to high latitudes, you also have during the winter months a phenomena that is known as the subsidence inversion. Now, this inversion is observed in mid to higher latitude. Higher latitude. In winter months. And that too in a region where there, there is a sinking air column. Why air actually sinks, we'll study in great detail in the next module. But wherever there is a sinking air column. So let's suppose you have we are talking about, let's suppose, the region around 50-60 degree north in the region of Britain. So during winter, the ground surface temperature will be very cold. So the air above the ground surface will generally be very cold, isn't it? So you have generally cooler air. Let's suppose in these, due to upper air disturbances, etc., in a region, if you have the sinking air, the air was cooler, it has started sinking, let's suppose. Now, as this air sinks, can we say it is coming into the region of greater density? It is falling into the region of greater air density. So, as it is falling into the region of greater air density, can we say there will be some amount of adiabatic compression? Isn't it? Some amount of compression will be observed here. This air will experience adiabatic compression. Adiabatic compression leads to what? Compression. So this adiabatic compression can lead to warming of air. Warming. Meanwhile, the ground was very cold because we are talking about higher latitudes, and that too in the winter months. Here you have colder air. So here you have the sinking air, which has created a higher temperature. Ground surface is very cold. So here you have colder air. So this is a kind of a negative lapse rate. It can develop only if the sinking air's temperature increases as compared to the ground surface. Sometimes it can happen that it warms up, but maybe it's still colder than the ground surface. But sometimes, as it warms up, if its temperature increases in comparison to the air near the ground surface, there will be a negative lapse rate. And this negative lapse rate is caused purely due to the process of sinking or subsidence of air. So that is why it is subsidence inversion. Okay, so that is the characteristic of subsidence inversion. We will study more about the factors, other inversion types, and discuss the PYQs, but we'll do that next year. That is on 2nd. And map pointing also, I will give you on Tuesday itself. Relax for the next 3 days. It is important to rejuvenate, recharge your batteries also. This is where we'll end the session here for today. I hope the next year brings with itself all the kind of hard work and the ability to commit the hard work. That is very important. So, all the best wishes. Do relax. Do try to reevaluate your goals, your purpose, and try to move ahead. Happy New Year in advance. That will be all from my side. Thank you for being very, very patient enough. We meet again the so called next year, but on Tuesday. Do take care of yourself. Goodbye. Thank you and have a good night.